Hey there, let's talk about 2D kinematics. Two-dimensional kinematics is much like 1D kinematics, except for there's motion going on in two different directions. What we typically do is rotate our coordinate system so that the acceleration lies along one of the coordinate axes and not both. To illustrate this, I'm going to solve a projectile motion problem. We'll start by drawing acceleration, velocity, and position versus time graphs for our specific system. Then we'll find the equations specific to our problem by relating the kinematic equations to graphs, and then we'll solve for unknown variables. We'll end up by discussing main concepts. This is a problem I'd like to solve. Package is launched at an angle from a pier toward an oncoming boat. The boat is moving at constant speed vb and is a distance d away from the package when the package is launched. Assume that the pier and the boat are at the same height. The time between the launch and the moment the package lands in the boat is given as Tp. Find the magnitude and angle of the launch velocity of the package. I've drawn a diagram here to where you can see that the total distance from the launch to the boat at the very start is d, and then the boat is moved from that initial position into the position where it catches the package. I'm going to start by listing the known variables. We know the velocity of the boat, the distance away between the pier and the boat at t0. We'll let t0 equal 0. And we also know the time that the package is in the air. And we'll let y0 equal y final equals 0. The things that we want are the magnitude of the velocity, or the speed, v0, and theta, the launch angle. I'm going to start by drawing kinematic diagrams in x and y. We'll do the acceleration, velocity, and position for each component. We'll start by drawing the graphs for the package, and we'll keep those lines in blue. The acceleration is 0 because we don't have any air resistance. The velocity is constant, therefore, so 0 acceleration means 0 slope on the velocity plot, and that also means that the x-plot has a constant slope. Now we're going to start our x0 at 0, so I've labeled our x position plot here. Since there's no air resistance, the acceleration in the y direction is a constant negative g. The velocity in the y direction starts out by being positive, stops at the very top of the trajectory, and then gets more and more negative. The slope of the velocity graph is going to be constant because the acceleration is constant. The position graph in y for the package is parabolic, concave down. We expect this quadratic function because of the constant acceleration. For the boat, we can see that the acceleration in the x direction is 0. It's going at constant speed the whole time. We also have that the boat has a smaller velocity, but also negative. It's going toward the package. The package is going to the right, boat is going toward the left, and we can see that the boat covers a smaller distance than the package in the x direction. That means that our boat has a constant slope in the position, and it has a less steep slope than the package does. The velocity, acceleration, and position are all 0 for the boat in the y direction because it isn't moving upward or downward. Okay, now, our main goal here is to find the magnitude of the velocity, so we want to find the components separately. We'll start by finding the x component of velocity. We start by looking at our general equation for v x final equals vx0 plus axt. Since the acceleration of the package is 0, we drop that term, and we can specify that the constant velocity of the package is the distance it travels divided by the time that it's in the air. I've drawn the distance the package travels onto the diagram. we can find that the distance that the package travels is the total distance the boat is from the pier minus the distance that the boat traveled while the package was in the air. And we can also find the distance that the boat traveled because we know its velocity is VB, that's constant, and also it's traveling at the same time that the package was in the air. So the distance the package traveled is the total distance d minus the velocity of the boat times the time of the package. So what I can do is I can take and divide that distance by the time that the package was in the air to find the initial velocity and the total velocity of the package. So now that we've found the x component of the velocity, let's go ahead and work on finding the y component of the initial velocity. To do that, I'm going to start with a general equation for the y component of velocity. Vy final equals Vy0 plus Ayt. In this case, we know that the acceleration is a minus g, so we'll set it equal to minus gt. At the top of the trajectory, our velocity in the y direction is 0. And also, we know we've gone half of the time, the total time that the package was in the air, so we can specify our equation as 0 equals Vy0 minus g times t package over 2. Solve this for Vy0, and we have the initial y component of the package. Now that we've found our initial velocity in the y direction, we can go on to find the magnitude. The magnitude of the velocity is just the square root of the sum of the squares of the components. Here I've just substituted in the values for the initial x velocity and the initial y velocity, squared those values, and then taken the square root of that. Notice my solution is completely symbolic. I have the thing that I was looking for, the magnitude of V0, equals an expression totally in terms of given variables. Now let's work on finding the angle theta. I can just use the theta equals arctangent of the y component over the x component of velocity because my angle is a standard angle with respect to the x-axis. And here I'm just going to substitute in my Vy0 over Vx0 to get an expression for the angle. So now I've found the magnitude of the initial velocity as well as the launch angle. I did it by first drawing the diagrams, the kinematic graphs, then I used those graphs to derive the equations, and then just solve them in terms of given variables. Let's discuss the main concepts of problem solving in 2D kinematics. First thing to do is carefully read the problem statement. Sometimes it helps to restate the main points of the problem to get solid on what's going on in the system. Pay special attention to multiple stages in the problem or multiple objects. Then the next thing to do is write down the known variables and the unknowns that I'm going to solve for. If there's not already a diagram of the system, I should draw one. The next thing to do is to draw graphs that represent the physical motion. In this case, that would be kinematic graphs. I need to think deeply about what's going on in the system, and again, recognize multiple stages or objects. They need to be represented in the graphs. I typically start with acceleration, then go to velocity and position. You want to keep the graphs consistent and draw one above the other to synchronize the time. Then I start with my general kinematic equations, and I use the graphs to specify the equations to my system. The next step is to do a symbolic solution in terms of given variables. This should take the form of my unknown variable equals an expression of only given variables. I want to watch for errors in algebra. It's a good thing to check units as you work. If algebra is a little bit challenging for you, you should practice symbolic solution even when you don't have to. In general, keep thinking about the system as you figure out what to do. Have a good idea of what's going on in the problem, and start with a roadmap of what you will need to do to be able to solve it. Well, that's kind of 2D kinematics in a nutshell. Thank you for coming. Come again soon.